In our last video, we cracked the structure of atoms. But how do these tiny particles create the 118 unique elements on the periodic table? And why do some atoms of the same element weigh differently? Today, we're diving into elements, isotopes, and the math behind your chemistry textbook's atomic relative masses. By the end of this video, you'll be able to define elements and isotopes, calculate relative atomic mass from isotopic data, and connect these concepts to real-world science like carbon dating. Now let's take a look at what elements are. An element is a substance made entirely of one type of atom. Each element has a unique atomic number, the number of protons in its nucleus. Let us take hydrogen as an example. Hydrogen has one proton in its nucleus. Therefore, its atomic number is 1. This means every hydrogen atom has exactly one proton. Now let's use carbon as our second example. Carbon has 6 protons in its nucleus. Therefore, its atomic number is 6. So every carbon atom has exactly 6 protons. Fun fact, the periodic table organizes elements by atomic number. Change the protons and you change the element. Let's explore the intriguing science behind isotopes. Did you know that not all atoms of the same element are exactly alike? Isotopes, for example, are atoms of the same element that have the same number of protons, but a different number of neutrons. Let's take carbon as an example. Carbon-12 has 6 protons and 6 neutrons. Carbon-14 also has 6 protons, but it has 8 neutrons instead. Both are carbon atoms because they have the same number of protons, but their different neutron counts give them unique properties. Isotopes have identical chemical properties like protons, but different physical properties like mass and density. Some isotopes are radioactive, like carbon-14, while others are stable, like carbon-12. Did you know that scientists can figure out how old a fossil is, sometimes thousands of years old, just by looking at the atoms inside it? That's where carbon-14, an isotope of carbon, comes in. Imagine you're an archaeologist and you found an ancient piece of a wooden tool. It's too old for anyone to know exactly when it was made, but you want to find out. The solution to your problem lies in the element carbon. All living things take in carbon from the atmosphere. The atmosphere contains a consistent, very small amount of radioactive carbon-14 alongside the stable carbon-12. So the tree had both isotopes in it. Once the tree was cut and used to make the tool, it stopped taking in new carbon. The stable carbon-12 stays put. But the radioactive carbon-14 starts to decay away at a predictable rate. It has a half-life of about 5,730 years, meaning that after this time, half of the carbon-14 will have gone. Scientists can take a tiny sample from the wooden tool. By measuring the ratio of the remaining carbon-14 to the stable carbon-12, they can calculate how many half-lives have passed. This measurement tells them how long ago the tree died, and therefore, how old the tool is. Let's now move on to calculating the relative atomic mass. Most elements exist as a mix of isotopes in nature. The relative atomic mass is the weighted average of all the isotopes based on how common each is. Now let's take a look at the relative atomic mass formula. AR is relative atomic mass. M is isotopic mass. A is percentage abundances of the isotopes. Let's go through a few examples together. For our first example, we are going to calculate the relative atomic mass of chlorine. To find the average atomic mass of chlorine, we use the relative atomic mass formula, which takes into account the masses and natural abundances of its isotopes. We will be identifying the isotopes of chlorine. Chlorine-35, with a mass of 35 and an abundance of 75%, and chlorine-37, with a mass of 37 and an abundance of 25%. Step 1. Plug in the formula. Step 2. Multiply the values. Step 3. Add everything together. Step 4. Finally, divide your answer by 100 to get the result. Example 2. Calculate the average atomic mass of magnesium. Remember, the average atomic mass of chlorine was calculated using the relative atomic mass formula, based on the isotopes' masses and their natural abundances. Now, let's identify the main isotopes of magnesium. Magnesium-24 with an abundance of 79%, magnesium-25 with an abundance of 10%, and magnesium-26 with an abundance of 11%. Use the relative atomic mass formula. Multiply the values. Add everything together and divide the answer by 100 to get your final result. All right, now let's try one together. We're going to look at boron. We'll go step by step to work out its relative atomic mass, just like we did with chlorine. Don't worry if it seems tricky at first. We'll talk through it together. Boron has two isotopes, boron-10 with an abundance of 20% and boron-11 with an abundance of 80%. Pause and try. Good job! So, the formula was applied, values were multiplied, everything was added together, and the answer was divided by 100 to get the final result. The average atomic mass of boron is 10.8 atomic mass unit, which is also the value shown on the periodic table. Let's go over the main things to remember from today. Here are the key takeaways. Elements are defined by their atomic number, protons. Isotopes are atoms of the same element with different neutrons. Relative atomic mass is a weighted average of all isotopes, explaining those decimal numbers on the periodic table. Next time you see the periodic table, remember, every number tells a story of protons, neutrons, and the incredible diversity of atoms in our universe. Stay curious and get ready to see how these elements combine to make compounds. Hello, learners. Feel free to drop by and visit our website for more free resources, worksheets, and tuitions. Visit us at www.anselhillacademy.co.uk today to get started, and subscribe for more updates, tips, and learning materials.